deep volumetric universal lesion detection using lightweight pseudo 3D convolution and surface point regression by Jinzheng, Ke Yan, Chi-Tung Cheng, Jing Xiao, Chien-Hung Liao, Liao, and Adam Harrison. Automate lesion detection is an important yet challenging task in medical image analysis. It is difficult due to the tremendously large appearance variability, unpredictable locations, and the frequent small-size lesion of interest. In particular, two key aspects requiring further research. The best means to effectively process the 3D volumetric data to more accurately regress the tumor's 3D bounding box. CT scans are volumetric, so incorporating 3D context is a key in recognizing lesions. As a direct solution, 3D convolutional neural networks have achieved good performance for long nodule detection. However, due to the GPU memory constraints, shallower networks and smaller input dimensions are used. 2.5D networks have been designed that use deep 2D CNNs with ImageNet's pre-trained weights and fuse image features of multiple axial slices. Nevertheless, these methods do not fully explore 3D information and also inefficient because they process DT volume in a slice-by-slice manner. So we propose applying pseudo 3D convolution to efficiently process 3D images. Good lesion detection also relies on accurate bounding box regression. Most existing anchor-based and anchor-free algorithms rely on features extracted from the proposal center to predict the lesion size. This is suboptimal since lesion boundary features should intuitively be crucial for this task. To this end, we adopt and enhance the representative point algorithm, which generates a point set to estimate bounding boxes. So different from representative points, we propose surface point regression, which uses an appearance regularization to force regress points to move towards lesion boundaries. Our proposed VLD follows a one-stage anchor-free detection workflow. VLD takes volumetric CT scans as input, extracts deep convolutional features with its backbone. The extracted features are then fed into VLD's 3D center regression and surface points regression heads to generate center coordinates and surface points respectively. We built VLD on DenseNet. Specifically, we first removed the false dense block as we found this truncated version performs better. We then use an feature pyramid network to fuse outputs of the dense blocks, which helps VLD to be robust to lesions with different sizes. We then investigate several different options for pseudo 3D convolution, which include inflated 3D, spatial, temporal 3D, and axial coronal sagittal 3D. The ACS 3D requires no actual model parameters, keeping the converted model lightweight. We then keep the front-end processing to 2D while only converting the third dense block of the truncated DenseNet to 3D using pseudo 3D convolution. This is because introducing 3D information at higher layer is preferred to lower layers. So for the first two dense blocks, the weight parameters are transferred from CL times Cin times n to CL times Cin times 1 times n to process volumetric data slice by slice. And in our implementation of ACS 3D, we empirically set the kernel number at a ratio of 80% by 10% by 10%, as the axial plane usually holds the highest resolution. Focusing first on the center regression head, it takes the output of FPN, also known as deep feature, and processes it with an ACS 3D convolutional layer followed by a fully convolutional layer. The output is a 3D heat map that predicts lesion centers. The ground truth heat map Y is generated as a Gaussian heat map with the radius in each dimension set to the half of the target lesion's width, height, and depth. We use focal loss to chain the center regression head, where M is the number of lesions in the CT, and alpha and beta are focal loss hyperparameters. We also exploit hard negatives by generating negative valued heat maps. Please see details in the manuscript. Once the lesion is located, its extent must also be determined. To do this, we directly regress a 3D point set using backbone features located at the center point, where n is the total number of points. This requires an ACS 3D convolutional layer, a fully convolutional layer, and a bilinear sampler. Because P is computed from the center point features, it may suffer from inaccuracies. Thus, we also compute offsets to refine P, where the delta x, delta y, and delta z are the predicted offsets of the refined surface point. To do this, for each location in P, we bilinearly interpolate corresponding backbone features and regress location-specific offsets. We then denote the ground truth bounding box using its top right front and bottom left rear corners. The regression of P and PR can be chained using the following laws. As for appearance regulation, the idea is to force surface point appearance to be more similar to regions inside the lesion than to those outside it. This constraint is achieved by adding a triplet loss with the lesion center as the positive anchor and the box corner as the negative anchor. With the supervision of points and appearance, we expect surface points will either move towards lesion surface or to the center. This constitutes our surface point regression. We optimize the surface point regression together with the center regression head by minimizing a joint loss function. Implementation details. We implement our system in PyTorch with 4 GPUs. The Pseudo 3D convolution backbone weights were initialized with the pre-chain lesion harvest weights. We also tried ImageNet pre-chain weights and random initialization, but performance was not as good. The FPN's output has 5 12 channels. In the task-specific heads, each ACS 3D layer consists of 256 kernels with kernel size of 3. The output channels of the lesion center heat map and the points and offsets and point-wise features are 1, 48, 3, and 128 respectively. We adopt the add-on optimizer and set a base learning rate to 1 over 10,000, which was reduced by a factor of 10 after the validation loss reached its minimum value. We also compare pseudo 3D convolution with 2D, 2.5D, and 3D lesion detection models, all using the same DenseNet backbone. The pseudo 3D convolution is superior in model size and speed. We evaluate our approach on 2 datasets, the open source depletion and a HCC-delivered dataset from the Chang'an Memorial Hospital. It has 574 dynamic CT studies. We randomly split the datasets for training, validation, and testing. We use 3D IOU with threshold 0.3 and FROC curve for evaluation. We first evaluate different pseudo 3D convolutions. We also test a bunch of state-of-the-art lesion detection models. To measure the impact of our proposed surface point regression, we also implement VLD with deep representative points that forgoes the appearance-based triplet loss. In Table 1, we compare our proposed approach against alternative methods. Using FRC analysis, Pseudo 3D convolution significantly outperforms the previous state-of-the-art Lesion harvester and Mulan by 4.5% and 8.5% respectively, which validates the effectiveness of Pseudo 3D convolution over its 2.5D counterparts. We also observed that adding the original deep representative points actually underperformed the baseline. This, in fact, motivated our development of surface point regression. While these results demonstrate the value of our pseudo 3D convolution backbone and the surface point regression, even more convincing conclusions can be drawn when analyzing performance based on lesion size. Our pseudo 3D convolution backbone can yield improvements of 7% sensitivity for small size lesions in deep lesion. Surface point regression can produce boosts in sensitivity of over 4% compared to direct sentinel style regression. These are clinically significant improvements. Visualizations and more visual examples can be found in our manuscript and the supplementary material. In this work, we tackle challenges of lesion detection in CT scans by proposing a very deep volumetric lesion detection model, VLD. It processes CT scans directly in 3D. It has very deep backbones with large capacities. The surface point regression head can effectively estimate the 3D lesion spatial extents. VLD also generalizes well with small-scale medical datasets. Compared with 2D, 2.5D, and full 3D counterparts, VLD is superior in accuracy, model size, and speed. VLD also achieved new state-of-the-art performance on the large-scale NIH deep lesion datasets. This is a work from PAI Labs. Thank you for your attention.